welcome back. Some more distributed loads for us today. This time we're going to solve some UDLs of different magnitudes, but with an overhang. So that is going to be the twist for today's exercise. But we know how to do this. Let's see together. So as we can see here, we have a beam. However, we have an overhang because we can see that the supports at A and at B are slightly internal to the whole beam length. Up until the first pin support at A, we've got a uniformly distributed load of 6 kilonewton per meters. Then we've got 4 meters in between two supports, between A and B. We have 9 kilonewtons per meter, and then we've got another overhang from B to the end of the beam with a different uniformly distributed load. So just like we did before, as long as we know that to find the equivalent force for a UDL, we just have to take the area of the rectangle and put it in the centroid, we're going to be fine. So let's start off by creating our free body diagram. So I'm going to replace this pin support at A with two forces, AY and AX, and this roller support at B with one force of BY. Now, just as a reminder, if I was going to draw the areas, I've got here this rectangle, then I've got here this rectangle, and I've got here this one. And each of these rectangles represent really the magnitude of the equivalent force. And each of these is going to be in the centroid of the shape. So one here, and one here. Let's call this shape 1, 2, and 3, just in case we need to clarify anything. So let's start off by solving our reaction forces using 3 equations of equilibrium. So I'm going to start off with sum of forces in x equals 0, with this being my positive x. So I've got ax plus nothing else in the x direction, so that's easy. Ax equals 0, and I've solved that. Moving on to the sum of forces in y equals 0, with this being my positive y. I've got ay plus by, those are the 2 reaction forces. They're both in the positive y directions, and now I need to figure out what the forces for each of these UDLs is. So starting off with what we called 1, I've got minus, because obviously this is in the opposite direction to my positive direction, 6 times 2. Then I've got shape 2, or that middle UDL, so minus 9 times 4. And then the last one is going to be minus 3 times 2. And that all has to equal 0. So if I solve that, I will find that AY plus BY equals 54. Now in terms of units, just to show you, here I've got 6 kilonewton per meters, and the 2 is in meters, so I can see that I'm left here with kilonewtons, which is a force, which is what I'm looking for. And the same for every other distributed load. My next move is going to be moments either around A or B. I'm just going to choose A in this case, and I'll use moments around B as a check. So if I start with moments around A, I've got BY contributing a positive moment, so plus BY times the distance from B to A, which is 4 meters. Then I've got the first rectangle number 1, which we called. Now that also contributes a positive moment around A. It's going to turn counterclockwise around A, so I've got another plus, and this time 6 times 2, that's the equivalent force, and the distance is going to be this distance here, right? So that is going to be 2 divided by 2. That's F1, and that's D1. Shape number 2, or rectangle number 2, contributes a negative moment, right? Because it's going in this direction and turning back to here, as opposed to this force which was going in this direction and turning back counterclockwise. So in this case, I've got negative 9 times 4, that is F2, and the distance is 4 over 2, right? It's this, to write in another colour, this distance here, that is D2. And my very last shape, that last rectangular force, is also negative, and it's got a force of 3 times 2, that's F3, the area of shape 3, and it's also got a distance, and in this case, the distance is this distance here. So up until here, I've got 2 over 2, and then I've got an extra 4, right? So times 4 plus 2 over 2, and that is D3. And all of that has to be in equilibrium, so all that has to equal 0. So if I calculate that, I've got 4 BY equals minus 12 plus 72 plus 30, so 4 BY equals 90, and BY equals 22 and a half kilonewtons. And now the last thing that I need to do is go back to this equation here and say that AY equals 54 minus BY, so that is 54 minus 22 and a half, and AY equals 31 and a half kilonewtons. And that's us solved all the reactions. We've checked the units, so that's fine. Let's do a quick sense check. AY worked out to be bigger than BY, and that makes sense, doesn't it? Because closer to A, I've got more load, because that overhang overhang close to A has a force of 6 kilonewton per meter, as opposed to the overhang next to B, which only has 3 kilonewtons per meter. So it does make sense that AY would be bigger in value than BY. The last thing I want to do before we finish is just a quick check. So I'm just going to delete these distances here. Everything else remains the same, like the magnitude of the forces and where their centroids are. But let's do a quick check by finding sum of moments around B equals 0, with this being the positive direction. So in this case, AY contributes a negative moment. So minus AY times a distance of 4. Then I've got a positive moment from that first rectangular force. So 6 times 2. Now the distance to B is going to be this distance here, call that D1. And that distance is going to be 2 over 2 plus 4. Then I've got the moment from the second rectangle. So it's a positive moment. 9 times 4 gives me the area. And then times a distance that is this distance here. So D2. And D2 is going to be 4 over 2. That's D2. And I've also got a moment from that third UDL, and that is negative. So minus, I'm just moving to the next line. 3 times 2, that's the force itself, and times the distance. In this case, the distance is this one here, that's D3, and that is going to be 2 over 2, so half of the length of 2. And all of that equals 0 because it's in equilibrium. So I get that 4AY equals 60 plus 72 minus 6. 4AY equals 126, and therefore AY works out as 31.5 kilonewtons. And that exactly matches what we got here by doing the calculation of moments around A, which means that I've checked my solution and it is correct. So the last thing I need to do is just replace these reaction forces with their values. So here at A, I got 0 for AX, so I don't need that, and I got that AY is 31.5 kilonewtons, and at B, I got that BY is 22.5 kilonewtons. And that's it. We've solved a beam with 2 overhangs with a slightly more complicated load because we had 3 different UDLs with 3 different values. But once again, once you understand the principle of it, it becomes much easier. So hopefully that's helped you with that. Let's meet again to solve some more things, but in the meanwhile, bye for now.